Alright, so let's just discuss some MCQs first. Let's see the homeworks. You did them? I didn't ask. Oh. Okay, last day it was a bit hurry, I think, the last moment, no? And I didn't ask you to do anything at all? Oh, good. So didn't you try any question from the tube? I think did I mention that you can I feel strange. Didn't I ask that to do all the questions? No? Not really? Oh, great. So you were like staying a single week without doing anything for the physics? Oh. So did they mention anything about that term tests or anything like that? Provincial tests? I think you had a provincial test, right? Last week, Thursday. How was it? Uh, I think the questions came only from the first unit, vectors and yes, okay. Schools have they finished it already? Yes. So they started linear motion then. I think there's a who's doing physics for you, madam, right? A miss, right? Nelum. Sorry, I don't know. Sorry, I didn't get it. Okay, okay. Doesn't ring a bell. Maybe she's new to the school. Okay then. Right. So we're gonna discuss some MCQs. Uh, First, we're gonna do the. Did we just see that whether we have done the seventh question on the page 8? Seventh question on the page 8. MCQs. Seventh question. Page 8. Did we do it? I think I asked you to do it, right? Yes, yes. How about you? Didn't you try? You tried. Okay. What's the answer you got? Sorry? Yes, 10 meters a second. Right. Right. So, what about how about the fifth question? No? I think I didn't ask you to do it, right? But you did, you couldn't. Second one. Okay. We'll see that then. We'll see the fifth question. I think. Where's your friend? The other one? He has a class today. Ah. Okay, okay. I think the bio girls are missing due to that. Maybe the bio classes it got extended a little bit. I don't know. They didn't mention anything about it, but it's okay. So we are kind of YouTube live as well right now. So we are live. So it's okay. Don't worry about it. Right. The fifth question. We're gonna try the fifth question. Fifth one. MCQ. Mm. So it says a trolley of mass m moves with a velocity u on a layer of ice. Due to falling of the rain vertically, water filled into the trolley at a rate of m0 kilograms per second. Okay. The time taken in seconds to reduce the velocity to v over 2, right? Okay. So it says something strange, mentions about a trolley moves on a layer of ice. Let's say this is the trolley. Doesn't mention anything about the mass of the trolley, so let's say it's to be the m, right? Okay. Then while it is moving forward with the velocity u, there's a rainfall. Maybe a huge rainfall, so that the water spills down and fills this trolley as well, right? Okay. So it moves a certain distance and takes a certain time for that. Let's say it took a time t. So during that time, the velocity should be decreased to v over 2. Why is it so? Because of this rainfall. It's a huge cloud, so it's falling the rain, and it is adding up the mass at a certain rate. See, m naught kilograms per second. What this one stands for? Kilograms per second means within 1 second it fills up this much of kilograms. I think you may have seen when driving the trucks and all, right? During a rainy day, the rain will fall into those trucks deck and they will fill it up, right? Then the same thing gonna happen in here as well. Let's say it took a time t for this one. So this much of kilograms is being added for 1 second. So if it took a time t, what will be the mass of the cart now? How do we find it out? We'll first find out, okay, mass of water fallen to the trolley in t seconds. How we can find it out? Well, we can find out m naught grams, m naught kilograms of mass in 1 second now into t seconds, right? So that I can get that one into m naught t. Okay with that? M naught into t, that's m naught t. I'll keep the unit for only for this one. After we can get it like that. So then what I can do, mass of the trolley after a time t. What's the mass of the trolley after a time t? Initially it had m, now we have m plus this fallen mass, right? What is that? M naught t. So it will be capital M plus M naught t, right? So it says that the rain is falling vertically down and it just adds the mass. So will there be an external force applied on this? No, right? There won't be an external force applied on this one. So in this case, I can write the momentum is conserved, so that I can apply the law of conservation of linear momentum. So let's apply law of conservation of linear momentum. So I just need to write the initial mass with the velocity. That should be equals to what? The final mass and its velocity. That's it, right? Mass into velocity. So I can apply to this side. That means second part I can add m plus m naught t times u over 2. Now you can see here we have a certain initial momentum. We're having a certain mass and a certain velocity. If the mass increases, what's going to happen? The velocity should decrease. Because let's say the initial momentum is 100. At the next case, we got this 100 from, let's say, 50 into 2, or maybe 2 into 50. What happens? This 2 increases to maybe 4. Then the other should decrease to 25 to get the same 100, right? Same as that, we had a certain initial momentum. Afterward, the mass increases, so the velocity should decrease to make the same momentum equal to the initial case. Right. So I can cancel off this u and I can multiply this 2 to this side, so it will be 2m. That's equals to m plus m naught t. So then m naught t is equals to capital M. So t is equals to m over m naught. Oh, the trolley of mass, simple M, right? Oh, I should have write it before. It's not capital M. Let's put it as a simple M as given in the question. That's simple M. Simple M U. Simple M this. Simple M this. And this. Just make the capital M to be simple. Okay. If you need, you can copy it down. Right, let's see the next one. We're gonna try the question number 11, MCQ 11. Did you try it? No? Okay, we'll try it now. Use a rough sheet. What's your name, by the way? Okay, just use a rough sheet. Ah, you have the ones I gave you last day. Yes, correct. What's the answer? 1 over 23. Okay, we'll see. Did you check with the answers from the back? No? Yes, exactly. So let me show you how we can do this one. Since you got the answer, it's all good, very good, right? With that, but let me show you how we can do it. Uh, so whenever you are given a question with this one, we first need to understand what sort of a scenario it is given, right? Whether it's a collision, or whether it's an explosion, or whether it's a mass moving on another mass, or maybe two masses moving apart. We have considered only 4 scenarios, right? So just see whether what sort of a situation given here, right? In this case, you can understand that this is been happening by what? The mass is moving on another mass, right? Yes. So it says like this one: when a child runs forward on a platform with a velocity 8 meters per second, the platform goes backward with a velocity 1 over 3. Okay. So let's say this is the trolley, or this is that what do you call the platform, right? Now the person is running on the platform forward with a velocity of 8 meters per second. This is the hand. 8 meters per second, which is the velocity. Let's say mass of that one to be the simple m, the other one to be the capital M. Then the platform goes backwards. It says the platform goes backwards with a velocity of 1 over 3. Yes. Okay. Now it's a matter of applying the law of conservation of linear momentum, but we need to make sure we should apply it to a certain direction, right? Okay. So initially m times u, which is m times 8, is equals to what? M plus m times 1 over 3, right? Because the child goes forward, and if you are wondering how you got this one, initially all them are at rest, 0. And while the child starts to move, m times with 8 minus, this goes backwards, actually it should be plus m times minus 1 over 3. This is how we got that. I can take it to this side, so, or maybe I can take this one to this side. So it will be 8m is equals to m plus m times 1 over 3. So we should find out the mass of the child, which is the simple m, over the mass of the platform, that thing. So we can see here the m's are for the both sides. Let me cross multiply that and make the capital M's to be one side and the simple m's to be other side. So it will be 24m, that is equals to m plus m. I can take this to the other side, so it will be 23m is equal to capital M. I should make m over m, so it will be m over capital, simple m over capital M is equals to 1 over 23, like that. Okay. Now we're gonna try the 13th one. 13th question. Okay, more sheets to do the drafts. Any clue that you do it? You got the answer? Which one? Fourth one. ML over M plus M. Okay. Okay. So check whether you got the answer with the same procedure, right? So there's a man here with the mass simple M, and the balloon is capital M, right? And this man starts to move upward, like just climbing up the string, right? He's moving upwards with the distance L, right? Need to move a distance L. So meanwhile, what should happen? The balloon should go down. Why is it so? Because this is giving up momentum upwards, which is not before initially. So to cancel it off, the balloon and the man should go down, right? Yes. So next, the thing, first you draw it, and then after you need to understand what sort of a scenario is this one out of that four. What is that? The mass moving on another mass, something like that, right? Because the man is just hanging on the rope. If the man climbs up, the man itself with the balloon should move downwards, right? Yes. So it's a mass moving on another mass. We understood that one. So what I can do, I can applying law of conservation of linear momentum. I'm gonna apply it upwards. So initially there wasn't any momentum, and finally what's gonna happen? The man starts to move upwards, so that the balloon and the man should move downwards. Let's say the man is moving upwards with a velocity of u, and the man with the balloon moves downwards with the velocity of v. So I can just write m times u minus, actually it should be plus m times minus v, right? So I can maybe write it like this way, the same way that we have wrote before, m times v. Then we haven't provided the u and v. So what we need to do? We should replace them with the distances. If you can remember, we have considered an example question like this. Like the one girl and a boy standing on a trolley, they pull them each other. So if one moves a distance x, the other one moves L minus x, something like that, right? And we have related the distances with the time. So what I can do here is I can write the u in terms of L, so it will be L over T. That's m plus m. How we can write the v? The balloon and the man has moved downward, which is the thing we should find out. X over, I can write the t. The t's cancels off, which we don't need that one. So we can subject the x, so it will be ml over m plus m. See how creative the questions are, right? Okay, okay. Now we're gonna do the 14th one. 14th question. The $1,000,000 question here is we haven't provided with any data like the velocity and all. By seeing at this diagram, you should have a conclusion. That's why. Think about it. Any guesses? Sorry? Second one. Okay. By the way, is that your friend doing bio? The other friend? Thanks. Okay. I'm just wondering what happens to that bio people. That's why. Okay. Okay. Uh, right. So it says something like this. Okay, there's a mass 3m moving forward, which means it should have an initial momentum to which side? To the horizontal direction, right? Since it is moving to this side, we should have a linear momentum to this side. Doesn't mention anything about the velocity arrow, just says like that. So the idea we should get is, okay, it should have horizontal momentum, initial horizontal momentum. But is there any vertical momentum initial? No, initially there's no any vertical momentum because it is not moving upwards or downwards, just horizontal to the horizontal side. Right. Now what happens? This got exploded and moves as three pieces. This is M and this is the other M. And this is the other M should be, but it's not given in the diagram. We have provided with only these two M's, right? So it says the one M is moving to this side and the other M was moving again horizontally. Then we're supposed to find what's the direction of the third mass, piece of mass. Okay. Now tell me, this is having an initial momentum to the horizontal direction. What can I say about considering these two particles? This is having again a horizontal momentum. Fine. But what about this one? It is inclined, so it should have two components. One is to this side, and the other one is to the upward direction. Right? If I resolve the velocities, one component should be horizontal, the other one should be vertical. Since the velocity is inclined. Then initially there was a horizontal momentum. Okay, so this makes sense, and this also should that should be there. But since this particle is moving to an inclined direction, it is gaining a vertical momentum as well, because there's a certain component to the vertical side which wasn't there before. So what should happen? To cancel off that final momentum vertically up, there has to be a momentum vertically down. So this should either have a velocity downward. Then what else? It could be moving to the forward or could be moving to the backwards, but seeing at the answers given, we can say that we can have assumption that it also moving forward while moving downward. So merging these two components, we can have a velocity to be to this side, which is very good. The second answer. If it was a guess, now it's time for you to make it totally clarified, right? Yes. Right then. Now we're gonna do the 24th question, the 24th MCQ, which is the last MCQ that we're gonna discuss today. 24th on the page 11. Don't you have the page 11? Oh, there are two 24th questions. Hmm? Oh, how that could be? Tell me how many pages that you have in your gift. How many? 16 pages. Yeah, okay. I also have 16. Do you guys have the 11th page? Nope. Page 11. Could I borrow one too? That's very strange. I think the printing shop messed up. Oh, okay. So the 24th question will be something like this. You can just refer that. Uh, yeah, guys, the online people, I'll just share the same question on the screen. Just give it a try. Okay guys, so the question is displayed in the screen. Uh, you can pause the video and try, then after play it. 24th question, this one. You can see with the colors if you need. Yes, any clue? Shall we try it then? Okay, okay. So yeah, as I have heard while listening to your discussion, yeah, it's kind of a little bit correct, because you can see here in this scenario the red color one shows the momentum of the A, right? So what's going to happen? The momentum of A slowly reduces. So what's happening here is it's just colliding with another particle B which is at rest. Which is at rest means the B doesn't have any initial momentum, right? So if I just draw this case on the diagram on the screen, let me switch the screens first. Okay, so there's a having a mass and having a velocity. Okay, it's drawn in the red, so let me use the red. Okay, this is the A and moving with a certain velocity, and the mass of that and the velocity of it, the product gives the P naught, right? Could be the initial momentum. And there's this guy B here at rest. So there's no any momentum for this one. So the initial momentum will be just P naught, right? Then after they collide with each other, the momentum of each particle P respect to the time is represented by, okay. So it doesn't mention anything about that these two get attached or something like that. But seeing at this diagram, you can see it is not being attached. They move as a separate pieces, right? Okay. Then this is the A and this is the B. Be like this. Okay. Now, if the A comes to 0, if the A comes to 0, which shows in this case, see, at the first case, and okay, this has to be the second one, right? And the first case, it seems that the momentum of A reaches 0, right? In the first case. First question it says, first choice it says the momentum of A becomes 0. If the momentum of A becomes 0, what should happen to the momentum of B? Initially we had P naught. So finally if this becomes 0, the other one should get that P naught. But seeing at the first choice, you can see the momentum of the B is given by this blue color. It hasn't reached the P naught, right? A way below than the P naught, which means the first choice is not coming, right? What can you say about the second choice? So in that case also, the momentum of A reduced, but not to 0. It's having a certain value, right? But the momentum of B eventually increased to P naught, but it is same as the previous one, right? It's the same as the previous case. Could be the second one. We'll see the third one. Can the third B happen? No, right? Why? We can see that the momentum of B has reached around approximately equal to P naught, but having a momentum for the A to be it's having a final momentum as well. It hasn't reached the 0, having a certain momentum. So the momentum of B cannot be reaching the P naught. Third we can remove. What about the fourth one? Yes, why? But you can see that the A has gone minus. And if it has gone minus, this should happen. Let me switch the cameras, right? I should do multitasking. I should see the cameras, Right, sorry for that. Right. Okay. Anyways, just see the graph like this. This is the P with the time, right? So you can see here uh, this is the P naught, and it has gone all the way negative like that. And the B here is going up even greater than the P naught, right? So still the gap has to be what? This is the initial part and this shows the final part. Initially we had only the P naught. So finally also the gap has to be P naught, right? So you could see here the gap is being the P naught, the same gap. But you can see the A has moved a little bit downwards. So that negative part has to be covered by the other one, which means you can see the same gain to the upwards, which is the fourth answer, right? You can still see the P naught gap. This is gone negative, so to cancel off the negative, the other one should go a little bit positive, right? So this is the most suitable answer that we could have. Yeah, it's kind of okay with the second one as well, but we are not pretty sure that this gap right here, this teensy gap, is being equal to the other gap, right? If the gap is same, fine. In that case, the second choice we could have something like we have got something like this, and this is the P and this is the T, and the P naught is the same, but it not reduced to exactly 0. We have the P naught here with the A, and B has gained the momentum, but you don't see the same gap with here. Got it? So the most suitable answer will be the fourth one. Got it? Great. So I just need to show you, whenever you are given a graph, you don't need to be like be scared, right, with that, right? And most of the students get messed up. Okay, what, like if it is given like a colored one, you can understand that, right? But in the exams, they are not providing any colored photos, so the questions will be like that in the given as in the table. So this will be one line, and this will be the other line. Sometimes the students mess up. This is one part and this is the other part. So these are the two momentums which are going down and the other one should go up. Okay, great. I'll print that page for you, right? As an extra page and give it to you. So you can, let's try one more essay question and we'll finish up this session. And I think you are holding up a curiosity about the cover page, the story of the cover page. Have you ever went through about it? You searched it? No? You have? Okay. You got the idea what has happened there? Ah, you knew it earlier. Okay, great. How about you? You searched it? Okay. You can know the story now. Uh, so we're gonna do one essay question, which is on the page 3. Question number 14 on the page 3. Yes, the rocket question. You can refer the note if you need, right? We have already considered about this one. Sorry. Uh, um, 2000. Okay, okay. So here not thousand, right? 10,000. Okay. Okay, just same answer, right? I think the zeros cancel, so. Okay, yeah, sorry guys, just 1 0 missing for each cases. Just 1 0. For the B 300, okay. Through 300, okay, okay. That's the one I messed up, right? Okay. So yeah, just 300. So 300, that will be 100 then. Is it? 302, okay, 600, so it will be 200 then, right? Oh, thanks. All right, meters per second. Divide squared and taking the root. So it will be 1000 squared over 3 squared, which is 9, plus 200 squared root. So what? I can take 100 out, which is root 10. 10 squared plus 2 squared over 9. Alright, 10 over 3. That will be 10 squared plus 2 squared into 9. So 10 over 3, 100 plus 36. I think there's no any root for 136, is it? Which is right here. Yeah, I can see that, right? Maybe I write somewhere else. Maybe here. Okay. Yes. Okay, you can take the root 34 to be 5.8. And simplify it up to the last decimal place. It's just 58 into 2 divided by 3. If you need, it's just 83. 5.83. Yeah, take it 5.83. Is it okay? You got this one to be like that? Nope. Well, let's just check then. We'll just check together. So we have. I can take 100 from this and 100 even from this, and gets the square. Okay, yeah. Square and square root makes 100 out, right? Yeah, it should be 100 out. Yes, 100 out. Okay, so it's 200 into this. So it's 583 into 2 divided by 3. Simple as that. Is it divisible by 3? So 128. No, it's not divisible by 3, but we can do it. 6, 6, 1 remaining, 11 divided by 3. So it should be 3, 26, so 8, 24, 2, 8, 24, 2, 6, 7, or maybe something like that. So we should find the resultant and also its direction. So let's just write this to be the alpha. So tan alpha here will be Vy or Vx. So alpha here will be Vy tan inverse 1000 over 3 over 200. 2 zeros cancels off. So I can write alpha. Alpha equals tan inverse 10 over 6. Right. Okay. Right then. So with that being said, we can finish off this part, right? The linear momentum, and the next thing we should discuss will be the center of gravity, right? Before that, let me tell you the cover story, right? It says something about that. Just see the cover story. If you have already heard of it, it's totally fine, right? Just see the cover story. You have the tune. What is that? It's something called DART. DART. What's the that's an abbreviation. What's the whole term? Yes. It says double asteroid redirection test. Okay. We'll first see what an asteroid means, right? So when it comes to this Earth, and not just around the Earth, around every planet, there are asteroids which are moving, right? Just parts of other planets, broken or maybe exploded planets. We say them to be the asteroids. So each of these asteroids has a specific path to move, right? Sometimes the asteroids move closer to the Earth. Sometimes they go very away from the Earth. And when they are going very closer to the Earth, we can see them very brighter. And you might have heard like a wishing star, right? In the cartoons and all, it just goes like this, like a shows a little explosion or something like that, right? Could be a asteroid, or maybe we say some there are other cases, meteoroids and all. So either way, let's say this is the Earth. This is the Sri Lanka, right? So when it comes to this one, this goes with a certain specific path. But sometimes there might be cases while going while the asteroid going its own path, it gets affected by the gravity of the other planets, right? Let's say there's this moon even. We're going to learn about this gravity, how the gravity works and the gravitational fields, how these are rotating around certain planets and all, in a future lesson, which we call as a gravitational fields, right? In that part, we can learn about it. For the time being, we know that the gravity try to attract things, right? So while this asteroid is going closer to the Earth, there might have a chance that it might get attracted towards the Earth, right? In that case, if that trajectory changes, that means the path of this asteroid changes, it's not going with this path, it may come up with like this and like this, and may end up with colliding on somewhere, right, on the Earth. So a similar thing happened before the extinction of the dinosaurs, right? I think you may have heard of this one. There were some dinosaurs, right, on the Earth millions of years ago, and there was an asteroid hit on the Earth, and it just destroys everything, right? Okay, so now what the scientists can do, they can predict the path of each asteroids, or we call as the near Earth asteroids, which are like which their paths are kind of aligned closer to the Earth, right? So there are some special telescope systems that are established around the Earth in different continents to observe the night sky and taking the photos. And while taking the photos, they can predict, like overlaying three photos together, we can see some moving objects, right? If the position of a certain a shiny dot changed, that means it has changed its position. Likewise, from around 60 years, right, from the past, around 60 years from up to now, they were observing this one, and they have found out there are some asteroids which are going very closer to the Earth, while some are going very far, right? And uh, one's very close by, and I'll show you a video. That's what I was watching while we were coming, right? Very closer years, around 2019, right? They predicted there's an asteroid that is going very closer to the Earth. But if the path of it doesn't change, right? If the path of it doesn't change, within, uh, as I can remember, within 80 years from now, from 80 years from now, there's a chance that this trajectory could go across the Earth. That means there's a chance after 80 years it might come and hit on the Earth, which is a like a future guess, right? Not a guess, but with the calculation, they found that okay, there's a chance, not right now, but after 80 years, right? So if there's a chance that we could change the trajectory a little bit, not much, but a little bit, it uh, may go somewhere else, so it won't fall into the Earth. So what they thought of doing, let's say while we are sitting on here, we see maybe a missile coming towards us. What we're gonna do? We're gonna either run, or if we need to defend the entire thing, and if we have some weapons to do, weapons to shoot, what we can do? Can grab them and shoot on the missile, and we can make it exploded before it reaching us, right? The same thing could done in here as well, but the thing is, this is an asteroid, so we can't just directly hit with a missile, right? Like maybe a ship, right? Maybe a plane or something, we can just hit on it, maybe a kafir or maybe anything. But this is an asteroid which is quite larger, and we can't just hit with a missile, we should shoot a rocket, right? Okay, that's the NASA guys came up with a brilliant idea, right? So let's say now this is the asteroid having a certain mass and having a certain velocity. So it has a momentum. So if there's a chance that we could change the momentum of this one, we could change its velocity. If the velocity changed, it may go with another trajectory, right? Another path. So what the NASA guys did, they launched a rocket. They launched a rocket with that. There's something called Falcon 9 rocket, Starship Falcon 9. Have you heard about them? SpaceX, the the one who's making Tesla cars, Elon Musk, right? So he has a company called SpaceX. So he's now kind of he's having a revolutionized company, right? To send people and the rockets to maybe to other planets and all. So he's trying up many efforts. He's putting up many efforts to build up good rockets. So with that Falcon 9 rocket, they have launched a little satellite. Right? I think you may have heard of this satellites, right? Something artificial thing that the people are making, but we can let it to revolve around the earth. We can let it to go around the earth, right? So what they did, they also launched a rocket and released a certain satellite like this. So the satellite also goes around the earth, right? And goes like this. And by changing its, we call the orbit, change in the orbit, they, what they did, they just made it to collide with the asteroid which is going closer to the earth. So let's say the asteroid having a mass and has a velocity, also this little satellite also having a mass and having a velocity, right? So what's going to happen once they collide? Will there be an external force? No, right? It's just the asteroid is going and the rocket hits or the satellite hits, and once it hits on this one, what happens? They will, both of them will move together, right? This is a very huge asteroid and this is a very little satellite. It's like the satellite fallen into the asteroid, which means two masses attached together. So initially this guy is having a velocity to this side, but once this one collides on this asteroid, there will be a portion of velocity getting added to this. So what's going to happen? The resultant velocity will be changed. Then it changed its course and it changed its path, and they estimated that now this asteroid is not falling to Earth for another 500 years. So for 500 years we are safe, right? So why we say it's double asteroid? So this is the first asteroid, and this is the other asteroid, that kind of artificial asteroid that the people have sent, right? So we have double asteroids. Redirection means it has changed the direction. Test. Why we say it's a test? Because they haven't done this one before. This is the first time they have tried it and they got it successful. Okay, let's see the video of this one. It's around 13 minutes, but I'll show it for you, and I share the YouTube link as well. You can watch that one and we can have a little break, and afterward we can continue with the next part, which is the center of gravity. Okay, let's see. Can I open it up? I will close this one to make it sure. Get down, right? Like watching a movie. Just opening up. The size of a refrigerator rammed into an asteroid at 6 kilometers per second. Launched aboard the fossil fueled powered Falcon 9, the dinosaurs finally clapped back. 66 million years after the asteroid had ended the dinosaurs, an unsuspecting asteroid was struck with an impact
3 tons of TNT, and we caught it all on film. This mission is perhaps the most important experiment NASA has ever performed. Data and information that could one day save us from the same fate as the dinosaurs. The asteroid we struck, Dimorphos, is 160 meters in diameter, much smaller than the 10-kilometer wide asteroid that exterminated the dinosaurs all those years ago, but large enough to unleash over 300 megatons of energy if it collided with Earth. 6 times more powerful than the most powerful nuclear weapon ever used. In the weeks since, scientists have been studying the results, calculating how effective our first asteroid redirection test was. However, the work that went into this mission far extends the last month of scientific study. For years, scientists and engineers carefully planned which asteroid to hit, how to hit it, how to confidently and quickly measure the effect of the collision. To understand the achievement of the DART mission, let's dive into the engineering and physics of its planet defense mission.
Okay, that's what simply
The
happened,
DART
right?
spacecraft itself posted no scientific instruments, designed to be a low-cost spacecraft, with just the tools it needed to complete its mission. Cameras to spot its target, star trackers to navigate through space, a propulsion system to direct it toward its target, antenna systems to speak with Earth, and an onboard computer, whose software has its roots in military missile technologies. However, DART did release a small Italian-made spacecraft designed to record the collision, giving us this footage showing a massive plume of debris being ejected from the asteroid on impact. The Falcon 9 rocket did the majority of the work in directing DART toward its target, Dimorphos. This was a unique target, chosen for a very important reason. It's a moonlet, a tiny moon orbiting the larger asteroid, Didymos. DART's camera gave us a glimpse of Didymos as it sailed by at a breakneck speed, closing down the remaining 920 kilometers in just 2.5 minutes. It computed and adjusted its trajectory using hydrazine thrusters, guiding the spacecraft to a head-on impact with the moonlet. In these final moments, DART shut down its thrusters, allowing the camera to take clear images of its impending doom, and giving us a clear picture of the rock we just obliterated 11 million kilometers away. So, why this rock in particular? There are countless asteroids orbiting the Sun. However, in order to study the results of impact, we need a specific kind of asteroid.
Okay, so it shows the trajectories and all, right? I'll share you the link of this video. You can watch it going home and maybe having a cookie and maybe having the evening tea, right? It's an interesting thing, right, to show you. And why I specifically showed you this one is the conservation of linear momentum or the physics that we are learning. It's not an alien thing, right? Or maybe it's not like a subject. It's not just a subject that we are learning. I just need to show you, even though it's NASA, right? Even though it's the outer space, the same principle used, the conservation of linear momentum. But there are a whole lot of other calculations as well. But the principal thing, the key thing that they learn that they used is, if there are no external force applied, the linear momentum has to be conserved. So what's going to happen? If we give a collision for this one, a collision could happen without an external force. So it could change the momentum, which it changed the velocity, so it changed the trajectory, right? So the little things that we are learning for the A levels could be applied even for the entire universe. That's what I need to say, right? Okay. So with that being said, I just need to show you again, I will just need to convince you that physics is something very interesting to learn, right? Rather than the other subjects, I'm not criticizing the other subjects, right? But rather than the other subjects, physics is much practical, and very critical to apply in the day-to-day cases, right? Okay then. Let's have a quick break and we can move into the next part of the lesson, which is the center of gravity. Alright then, back to the lesson. So we're gonna start the new part. We write the topic center of gravity. Center of gravity. Okay. So as always, I just need to know what's your opinion about this one. What do you feel when you say the word center of gravity? Yes. Any idea that comes to your mind? Seems like doesn't ring any bells, right? Okay, so which could be a new part then. I think you may have heard of this already, like the word, like just the word, the center of gravity, right? Uh, so it's the simplest idea that we can say. It is the point where the gravity acts on a certain object, right? So we know we are on a space that the gravity works, right? That is why if you just drop something, it falls down, right? That's due to gravity, right? Okay, so whenever we are on a gravitational field, right now we are in a gravitational field. When any object is on a gravitational field, the gravity works, right? So if you could just point out a single point where the gravity acts on a certain object, we can represent that to be the center of gravity, right? And it's not a like a point that we could see from our like eyes, like just seeing at this duster. Okay, this is the place the center of gravity is. You can't say like that, right? It's just an imaginary point that represents the total gravity acting at a single point, right? It's not a point that we could see observing the object. We can't see where the center of gravity is, right? So what it explains, like a mean point where all the gravities, all the gravitational force being acting on a certain object, right? Simple as that. Okay, so we'll write a little note and we'll find out the main thing that we are going to do here is finding out the center of gravity of certain objects, right? And again, this is a little foundation for a big castle that you're gonna build later on for the applied maths. Why? Because there will be a huge lesson for the center of gravity, right? Once you learn Still, you are maybe learning about the trigonometry and maybe something about the limits. I don't know whether you have started limits. Have you? No, not yet, right? So once you start with the limits, the differentiation and integration, those are the giants of the maths, right? The combined maths that you're gonna learn. But bio guys, don't worry about it, right? Still, it's a little foundation because there will be a huge question. There will be an entire question that comes for the gravitational, the center of gravity in the applied paper, right? For that one, this will lay a little foundation, and for the physics, we just need to learn all the concepts behind the center of gravity and how we can find that one out in an easy manner, right? Okay, then we'll write. We write like this: every object has made, every object has made by combining, tiny pieces of masses together. Tiny pieces of masses together. The addition of the addition of all these masses, the addition of all these masses gives the mass of the entire object. Gives the mass of the entire object. The point where the mass acts, the point where the mass acts on a certain object, point where the mass acts on a certain object is called its center of mass. Is called its center of mass, which can be defined in a field where the gravity may or may not act. In a field where the gravity may or may not act. Okay? May or may not act. Finished? Right. We write in a new paragraph. The point where the weight acts, the point where the weight acts on a certain object. Weight acts on a certain object is its center of gravity. Is its center of gravity, which can be only defined in a gravitational field. In a gravitational field. Can be only defined in a gravitational field. In a new line, right? For the masses, comparatively smaller to the size of the earth. For the masses comparatively smaller to the size of the earth. Size of the earth. The center of mass and the center of gravity lies on the same point. Center of mass and the center of gravity lies on the same point. For the time being, you might not get this one much clear, right? What is the center of mass and center of gravity? I'll just give a basic idea. I think you already know what the center of gravity means, right? So if I just take this duster, right, what I can do, I can represent the duster as a combination of smaller masses, right, that are stacked together, right? What I can do is I can even tear a piece of it like this, right? So the duster itself makes of these tiny particles, right? Each of these particles has a mass. Also, it has a weight. Why it is having a weight? Because if it is having a mass and if it is on a gravitational field, it just has a weight, right? Okay. So let me draw the duster in the tape on the board, right? It will be like this. This is the duster, and it consists of little masses like this. And seeing at this mass distribution, we can represent a mean point for all these masses, which is called as the center of mass. Right? Seeing at the distribution of the masses, I can say, okay, this is kind of the middle point for all the masses of this duster. That is called the center of mass. When it comes to center of gravity, it's just like this. So let's say this is having a mass of m1 and having a weight g. So it will be m1g. M1g, right? Another particle is having a mass m2 and has a weight of m2g. This is m3g, this is m4g, m5g, m6g, right? Likewise, we have several trillions of tiny particles that ultimately makes the shape of this duster, right? Each of these has a weight. So if these tiny masses makes this duster, what I can do, instead of pointing out the weights for each of these tiny masses, I can represent a mean point to represent all these tiny weights. That is called, let's say the total mass of this duster is capital M. So I can mark the point to be the G, which is the center of gravity, that represents the weights of all these tiny masses, which ultimately makes the duster, right? That's the whole idea. So when it comes to center of mass and center of gravity relative to the earth, right, relative to the earth, we are kind of comparatively very small, right, considering the size of the earth. So in that case, the center of mass and the center of gravity will lies on the same point for every tiny masses that are on the earth's surface, right? So it could differ when we are considering about, let's say, the earth and maybe the sun. This is the sun, which is very larger, and this is the earth. When it compared with these large sizes, the center of mass and center of gravity of these two guys, there's a center of mass for these two, sun and earth, but the center of gravity, kind of weird to explain, right? Because the sun is also having its own gravitational field, the earth is also having its own gravitational field, so it's pretty hard to define which is the center of gravity between these two cases, right? Which we can go through in a future lesson. As I told you, we can learn this one for the gravitational fields. right? For the time being, we need to know we are dealing with the things on the earth. So the center of mass and the center of gravity lies on the same point. That's pretty much it. Okay, let's write a subtopic: properties of center of gravity. Properties of the center of gravity. Properties of center of gravity. ඊරස් කරන්නේ 12 13 මලින් කවුරු හරි ඇවිල්ලා මම මොන සර්ට පහට කියන 12 මාරනේ තියෙන්නේ ඔව් 12 මාර 4ද 12 මාර 12 මාර රිවිෂන් ගන්න සර් ඊට පස්සේ ඔයගොල්ලෝ චෙක් කරනවා මානියන් කියන්නේ right, we'll write the first property. When a uniform object is considered, the center of gravity lies on any considered symmetrical axis. For any uniform object considered, the center of gravity should lie on any considered symmetrical axis, right? Okay, what that one means, let's consider a kind of a uniform object. What is said to be uniform? Could be a triangle, rectangle, right? Having a finite shape and to be regular one. When it comes to this duster, it's not pretty regular, right? But when it comes to this phone, it can be said to be regular, but not much, because we have the cameras and all right down, which is kind of not balancing up. But if it is a balanced scale, I can't see any proper yeah, I don't see any proper maybe this one, right? It's having a finite shape, and you can see it's kind of very symmetrical, right? So what could be the symmetrical line here? You can just draw a line in the middle, right? So the center of gravity should lie on that symmetrical axis. When it comes to triangles and rectangles, or maybe any regular shape, the center of gravity should lie on all the symmetrical axes that we can draw. Let's say the symmetrical axis is like this, so the center of gravity should lie on that. If I can draw another symmetrical axis like this, the center of gravity should lie on that axis as well. So what's the best point that it could have? The intersection of the 2 points, right? Okay, so this is the place the center of gravity should be. And when it comes to a circle, so if I could just draw a symmetrical line like this, the center of gravity should lie on this. And if I could draw another one, it should lie on this. If I could draw another one, that should lie on this. So the best possible case will be the middle, right? Could be the center. Okay, just draw it and mark there. Right. So we write at the next point. The center of gravity is relatively stationary. The center of gravity, is it a ghost? Okay. The center of gravity is relatively stationary to a certain, to the object, to the object. The center of gravity is relatively stationary to an object. That means when it comes to this, let's say the center of gravity maybe lies here, relative to the object, it doesn't move, right? When the object moves, the center of gravity also should move, right? Relative to the object, it should be stationary somewhere in a certain point on the object. On the object. Okay, let's try the next point. Next property actually. Third one, I'm guessing. Yes. The next one, the center of gravity could lie. The center of gravity could lie on or away from the boundary of the matter, on or away from the boundary of the matter of an object. Boundary of the matter of an object. Right? So let's say this is a circular disc. Then where should be the center of gravity? Should be in the middle, right? The very center, because I can draw dozens of symmetrical lines. So all those lines should merge with the center of gravity. Now let's say, suppose this one to be a ring, like a donut or maybe a ring. When it comes to a ring or a bangle, whatever, pens are not working. Okay. When it comes to a ring like this, where's the boundary of the matter? I mean, in this case, the boundary goes in a circular path, like what is the boundary here? This case, you can see only the matter on this part. Do we see a matter inside? No, if it is a ring, you don't see any matter in the middle. But still, the center of gravity should lie on the middle. So the center of gravity in here, in this case, it should lie on the boundary of the material. But here, the boundary of the material is like this, but the center of gravity would lie away from that. So when it comes to maybe a rod like this, a uniform rod, the center of gravity should lie in the middle again, the center. But when it comes to a curve, or maybe if I could bend, if I could just bend the same rod, where should be the center of gravity? It should still at the same point, right? So what we can say here is the center of gravity, regardless of whether it is inside the boundary of the matter or maybe outside, it could be staying in a certain object, right? Let's draw it. This is a disk and this is a ring or uniform rod. Okay, the last point, you're right. When system of particles, when system of particles is considered, when a system of particles is considered, the center of gravity, the center of gravity should lie closer to the higher mass. The center of gravity should lie closer to the higher mass. Okay, let's say we are going to consider a system with just two particles, just two, maybe two balls, right? Like that. So, the center of gravity of these two particles, since the masses are same, the center of gravity should lie perfectly in the middle, having the length to be 1:1, right? But when it comes to a smaller mass and a higher mass, maybe 3m and m, in that case the center of gravity should be closer to what? Closer to the higher mass, which means there's a higher tendency that the center of gravity should go towards that, which is this. So the length will be, now in this case the masses were 1:1, so the length was also being divided to 1:1, but here the mass ratio is 1:3, so the length ratio will be 3:1. Let's say this is like having 3 meters, so this should be having 1 meter, something like that, right? Okay, I just draw it too, and that's the last thing that we're gonna write for today. While you're drawing, guys, are you doing the same? Are you doing the questions also on the same book? Okay. Right? Okay then. So the next day onwards, what we're gonna do will be, we are going to find out, we're gonna learn how to find out the center of gravity of certain uniform objects, right? So let's say this water bottle, right? We're gonna learn how we can find out the center of gravity of this one, and also this duster. It's not regular one, but we can find it out, right? Even some very complex shapes, like maybe okay, maybe like this. This rod is being connected to this, maybe somewhere here, right? So we're gonna find out the center of gravity of this entire thing, this rod and this rod together, right? Maybe like different shapes, right? We're gonna learn how we can find that one out. For that, you should have a little idea how the moment works. We have already considered what the moment is, and if you don't have any idea, please make sure just refer some O-level notes about that. And for the A-levels also, we have considered about it, right? What's the moment basically? Mass, the force into, yeah, the distance. Simple as that, right? So we should know about that one to proceed. So I'm leaving you the first part of these tudes, right? Because I couldn't ask you to do them. So now we have some homeworks to do actually. We can finish up all the questions that are there for the linear momentum, right? The essay questions and also the MCQs, right? Finish that one off and let me know if you have any doubts before the class. Just send me a WhatsApp message or something like that if you find any doubt, so that I can clarify it to you before the class. And let me know if I need to change the teaching pattern, or maybe if I'm too far or too fast or too slow, like that, right? Just throw me any comments, then we can fine tune the class. fine tune the teaching and learning pattern. Right. Then we'll wind up for today. Thank you for joining the class and see you very soon. See you then. Have a good day.